Good afternoon, all. Last day we have learned about the powered series and two important powered series, the Taylor series and Lorentz series we have learned. Today we have the convergence of powered series we have to learn, where it converges, the circle of convergence and the radius of convergence, and we have one more concept, the uniform convergence of the powered series. First, the convergence and absolute convergence of powered series. We have a theorem. If a powered series sigma n equal to 0 to infinity an into z minus z naught raised to n converges when z equal to z1, z1 not equal to z0, then it is absolutely convergent at each point in the open disk mod z minus z0 less than r1, where r1 is equal to mod z1 minus z0. Now, based on this theorem, we have the region of convergence called the circle of convergence. The greatest circle centered at z0 such that the series sigma n equal to 0 to infinity an z minus z0 raised to n converge at each point inside. It is called the circle of convergence, and radius of that circle is called the radius of convergence of the series. Now we have the formula to find the radius of convergence. Radius of convergence r is equal to 1 by limit supremum n tends to infinity mod n raised to 1 by n, and we have one more formula, limit n tends to infinity mod n by n plus 1, mod n plus 1. These formulae are known as the Cauchy-Hadamard formulae. Now we have 4 problems to find the radius of convergence of the power series. First problem is sigma n equal to 0 to infinity z raised to n by n factorial. Second problem, sigma n equal to 0 to infinity 1 plus 1 by n square all raised to n square, 1 by n all raised to n square z raised to n. And third problem is sigma n equal to 0 to infinity n factorial by n raised to n z raised to n. Fourth problem, sigma n equal to 0 to infinity n raised to n z raised to n. Now we can do these 4 problems. The first problem is find the radius of convergence of sigma n equal to 0 to infinity z raised to n by n factorial. So here an is equal to 1 by n factorial. So we can use the second formula, limit n tends to infinity. So an plus 1 is 1 by n plus 1 factorial. So radius of convergence is limit n tends to infinity mod an by mod an plus 1, which is equal to 1 by limit n tends to infinity 1 by n factorial by 1 by n plus 1 factorial, which is equal to limit n tends to infinity. This we can cancel, the term is n plus 1 and it will goes to top. So this is infinity. So the radius of convergence is, of the first radius of convergence is infinity. Now the second problem is, second power series is sigma n equal to 0 to infinity 1 plus 1 by n all raised to n square raised to into z raised to n. So an is equal to 1 plus 1 by n all raised to n square. So we can use this first formula. So an mod n raised to 1 by n is 1 plus 1 by n all raised to n square all raised to 1 by n, which is equal to 1 plus 1 by n raised to n. So we can, radius of convergence is r is equal to 1 by limit supreme n tends to infinity 1 plus 1 by n all raised to, so this is in denominator, 1 plus 1 by n raised to n. So this is limit n tends to infinity 1 plus 1 by n raised to n is e. So the answer is 1 by e, since limit n tends to infinity 1 plus 1 by n raised to n is equal to e. So therefore the radius of convergence is E. Now the third problem is sigma n equal to 0 to infinity n factorial by n raised to n z raised to n. Here an is equal to n factorial by n raised to n. So n plus 1 is n plus 1 raised factorial by n plus 1 raised to n plus 1. So the radius of convergence is limit n tends to infinity mod an by mod an plus 1. So which is equal to limit n tends to infinity n factorial by n raised to n by n plus 1 factorial by n plus 1 raised to n plus 1. So this we can cancel. So this is n plus 1. So this is which is equal to limit n tends to infinity. This is 1 by n raised to n. Here it is 1 n plus 1 raised to n plus 1 into n plus 1 raised to n plus 1. So this we can cancel, and this is n plus 1 raised to n. So this is we could write this is we can take the n plus 1 raised to n to top. So limit n tends to infinity 1 by n raised to n into n raised to n into 1 plus 1 by n raised to n. So this we can cancel, and the answer is E. So the radius of convergence is E. Now we have fourth problem. Fourth problem is sigma n equal to 0 to infinity n raised to n z raised to n. So we can, here the power is there, so here it is n is equal to n raised to n. So r is equal to 1 by limit sub n tends to infinity mod n raised to 1 by n, which is equal to 1 by limit sub n tends to infinity n raised to 1 by n, which is equal to 1 by limit sub n tends to infinity n raised n, which is equal to 1 by n. Limit n tends to infinity 1 by n is 0. So the radius of convergence is 0. Next concept is uniform convergence of power series. We have a power series sigma n equal to 0 to infinity n into z minus z naught raised to n, and we have a circle of convergence mod z minus z naught equal to r, and the two sums, the sz represents the sums and the partial sums is s and z, that is s of z equal to sigma n equal to 0 to infinity n into z minus z naught raised to n, and s and z equal to sigma n equal to 0 to n minus first n sums n into z minus z naught raised to n mod z minus z naught less than r. Now define the remainder function as rho n z, which is equal to s n z minus s of z. Now by definition of limit of a sequence corresponding to each positive number epsilon, there is a positive integer n epsilon such that modulus of rho n z less than epsilon whenever n greater than n epsilon. When the choice of n epsilon depends only on the value of epsilon and is independent of the point z taken in a specified region with the circle of convergence, the convergence is said to be uniform in that region. This is the definition. So the uniform convergence is defined in the power series, and that the convergence, the limit modulus of rho n z less than epsilon, that depends only on the value of epsilon without the choice, independent of the choice of z, then it is called the uniform convergence.